Hello all. Today I
Oh,
have immense pleasure of having on air Aaron Wilson from the Idaho Lab. Aaron, how are you doing? How is everything on the
not
other
bad.
side?
I'm having a great day. Going well.
Aaron is a research scientist in the Idaho Lab. And can you please explain to us a little bit more about what is the Idaho Lab and your role in it?
Absolutely. Idaho National Laboratory is we're having our 75th anniversary this year.
Oh,
And
congrats.
when the US decided that they were going to start building nuclear reactors, they figured Chicago wasn't the best place to do it. And so in terms of the nuclear power, it started at INL. So what the precursors to what INL is. The first place lit by nuclear power was ARCO, which is across the desert from Idaho Falls, where I am now. And it was built on this area that was owned by the Navy. And since then, we've built 50 plus reactors here, including the the pilots for the initial aircraft carriers and subs and whatnot. And so that's what we were founded as. Since then, we've really developed into a multidisciplinary lab that includes three major directorates: a nuclear energy directorate, a homeland security directorate with a fabulous cybersecurity program, as well as an energy and environmental science and technology directorate, which is where I'm located, and building off of kind of our history in nuclear power and the mineral recovery that goes into the DOE program. So the Department of Energy was built off of the Manhattan Project, which had an element of creating a device, but then the other half of the element was obtaining minerals and materials to make that device work that had never been obtained before, and we developed a lot of separations in that effort. So
Yeah, yeah. And you have put a lot of effort into the latter, right? As in your role in
yes,
the Idaho Lab, if I'm correct.
so so I've been with Idaho National Lab for almost 15 years now. Um, I'm a chemist by training, and here I've worked in two highly related areas: water treatment and mineral recovery. Currently, a lot of my work is focused on. I do work for the Critical Minerals Innovation Hub, and I'm a center lead, a co-lead uh, for the Separation Center in the recently funded metallic effort, which is a $75 million effort to facility dedicated to getting hard to test mineral recovery within the DOE system and help advance technology through having a almost user facility for mineral recovery development efforts. And so that's a couple of the things that my roles here and a couple of the projects I'm working on. So
Lots of interesting work ongoing in Idaho. Yeah, that's for sure. So you and me, we are both, let's say, advocates of brine valorization, of
absolutely.
different streams, yeah, of different salinities. Do you think, first of all, that it is feasible?
To valorize brine. Yeah, absolutely. I think there's a really classic example. So magnesium until the mid 90s was made from seashells and seawater at the at the Dow Freeport facility in Texas. And it's so and that was stopped because of economic reasons, because the Chinese started making magnesium out of coal and dolomite. And whether or not that was a cost-driven effort in China is it's a constant question. It's the free market in the mineral business is not free across the spectrum. And so that's something that a lot of the mineral recovery space is dealing with, is that it's not driven by the cost of processing material, which if some companies are driven by that, it means that they have a challenge surviving. But that's a prime example where until very recently, that was the source of a mineral, was actually seawater. And then we can point at many other places where we see the lithium coming online, where lithium can come from spodumene, mineral that's dug out of the ground, acid leached, and then treated, or it can come from brines, and we can do direct lithium extraction on those brines. And those are the two of the most visible examples. But there are many places that are a little less flashy, but just as important where the techniques of water treatment are both addressing the waste concerns, which are also massive. So there's two sides to the coin. We don't want huge amounts of liquid waste going into the environment. Indonesia has had an issue with their mine waste going directly into the ocean, and we need to develop technologies where we don't do that, where we are treating that waste, but then also recovering the minerals at the same time. It's a benefit for both sides. And yeah, so we have a great deal of tailing. Oh, go for it. Go
Yes.
for it.
So essentially, brine valorization can happen with the technology
Yeah.
that we have. And currently, as I see it, there are more than financial reasons to do it, such as strategic reasons, CO carbon footprint reasons. Yeah. So we need to
Yeah.
take into consideration these parameters also when we are addressing this issue. And prior to our online conversation, as you mentioned, it's not about minimizing the liquid streams. The priority should be to recover the valuable components therein, right? This
I
is the
I
priority.
think they're both factors. They're absolutely both factors. It's we want it to be cost effective. And sometimes being cost effective is minimizing the liquid stream. So creating water that can be reused in the process and taking it from a 20% fraction that is like some intake water where you recover 80% of the water for in process or whatnot, and you're discharging 20%, taking that down to a very small percentage where it's sent to I mean, ideally, where you're generating solids that have value, or solids that can be basically landfilled. I mean, the big challenge here is the sodium chloride. Almost all the other minerals out there have value, have commercial streams that they can be absorbed into. The calcium, the potassium, the sulfate, the carbonates, the magnesium, and all of the lower concentration materials. Every single one of those has a commercial stream where they could be sold into. The sodium chloride has value too, but there's honestly only so much hydrochloric acid, chlorinated plastic, hydroxide, sodium hydroxide that we need in any one region around the world, and there's a scale issue. We need a lot more water than we need those products, so there's going to be a disconnect there.
Do you think that there will be a way to bypass the whole issue, or do we always have to go through sodium chloride to get to the more interesting materials?
That's an interesting question. So can we basically grab the valuable materials out and leave the sodium chloride in the stream to pass it into maybe a more conventional discharge path, like down, whether it's kept low enough that it can go into a river or deep well injection or into the ocean or into a landfill. I mean, like those are kind of the options that are out there, with the landfill being something that's done on a very limited basis. I think so. I think there are places that like direct lithium extraction, DLE. I mean, that's the goal right now. There's efforts to do that, and we can probably do that with more minerals. I mean,
Okay.
nanofiltration for a long time was considered a more expensive, less effective um, technology, but it's now becoming commercially viable. Like people are really taking it seriously in a commercial environment, and that's exciting because what that gives you is a divalent stream, which is where a lot of the value is. A lot of the value is in the divalent plus the polyvalent stream. Whether it's like a transition metal or a rare earth, that they're going to be captured pretty well by a nanofiltration concentrate. So
And proves that we may have tools already in our toolbox that we have may overlooked, right? We
yeah,
don't really know
absolutely.
all the applications that could potentially be brought up with for our needs.
Yeah.
Please.
Yeah, so I was just at the last week. I was just at the Critical Materials Innovation Hub meeting in Ames, Iowa. That's Ames National Lab, and we had several different talks on critical materials recovery flow sheets. And so in water treatment, we understand that it's a multi-step. It's a treatment train, is the way it's often described, where you have pre-treatment. Let's just stick with like a desal type approach. You have a pre-treatment where you address scalants, you address the biology that could foul the membrane, or anything that could damage the RO membrane, essentially. And that train can involve adding chemicals. It can involve filtrations. It can involve a variety of things, from UF to NF to biocides to anti-scalants to whatnot. There's steps there, and there's actually a lot of room for innovation there, because that varies a lot from place to place to place. But then you have the reverse osmosis step, which is it can be a brackish water, just a seawater membrane, and you do that, and then sometimes you got to do mineral remineralization at the end of it. So that is a pretty simple treatment train compared to mineral recovery. The flow sheets for mineral recovery are massively more complex. They have 5 to 6 times more unit operations. And there's a number of places where the techniques that are really pioneered in desalination could be transferred into mineral recovery. And a lot of this might require more robust membranes that can tolerate pH, low pHs primarily, that can tolerate the presence of a fair amount of organics in the system. Because if you have a solvent extraction process in the system, that's an issue. If you're addressing waste from something like coal fines, you also have a fair amount of organics in the systems. And there's massive water issues with coal fines. One of the greatest challenges with mineral recovery is, where do you put the waste? The rule of thumb is you can send it to a slurry pond for $10 or 10 cents, 10 cents a cubic meter. 10 cents a cubic meter, you can send a waste to a slurry pond. That can be a tailings pond, that can be fly ash, that can be coal fines, that can be red mud, bauxite residue from aluminum processing. All those things can go to slurry ponds, except there's a great hazard with that, because those things can have leaks over time, and they can also have catastrophic failures. Recently in Brazil, there was in 2015, there was a catastrophic failure in a mine in Brazil, run by a major mining company, that killed people, and the Brazilian government just levied a fine against that event on the order of $9.7 billion. It would have cost them $500 million to treat the material that they lost control of. And so that's say 20 to 1. It would have been a major savings. Hindsight, that is what it looks like. But what that does is it informs what people might do in the future. If you don't treat your water, if you don't go from wet storage to dry storage, there's an issue. There's potentially an issue down the line. There's a risk, and so that's both a water treatment, but also it gets into the mineral recovery space for water, because it goes all the way to solids, and that's where this mineral valorization has to do. It can't just do the liquid-liquid separations. It's not enough to get a stream of like sodium chloride or fresh water, a stream of liquid sodium chloride. You also have to get the solid lithium out. You've got it as a salt, as a hydroxide or carbonate. You have to get your battery metals, your nickel and cobalt sulfates out as solids, or your rare earths, or your potassium sulfates or nitrates, or whatever those are that have value as fertilizer. That you have to get those out as solids somewhere in the process, which means we need to look at a few more transformations than we might normally look at in water treatment. So, yeah.
According to your opinion, we are both fellow experts on brine,
Yeah.
concentration, polarization. Which will be the critical parameter that will turn the market to this direction? Will it be because let's face it, politicians are not gonna put money on this unless the level of the problem is pretty high.
Yeah.
Um, and you also have the material issue, yeah, strategic needs. But will it be, for example, potentially also the application of scale? Yeah, because it makes things more easy on large volumes, which, according to you, will be the turning point.
So uh, we can look back at other technologies that have been successful. Um, and I think the classic example that the US can point to is the reverse osmosis membrane. And we can walk through that. There is a good sustained basic research effort for a long time. And so this something that I recently talked to one of my industrial friends about at a company that has water interests is he thinks that the national labs and universities should not try and do what industry does. We each have a different purpose. And our role is to get the water treatment, to develop technologies to the point where industry can take they can be handed off to industry. And so I think there is a role for public support of foundational research and to avoid premature partnering and to do the full process, not just fundamental research, but to get it maybe not up to the pilot scale, but to get it up to the point where the technology has been demonstrated to the point where we're here like, okay, let's bring in an engineer to automate this. Like we've seen it, we know all the separation effects, we know all of this, and now we need to start doing it at a slightly larger scale. We've done it with small modules. We've taken Sterlitech systems and done it with spiral wound modules or hollow fibers or whatever it happens to be at the is it 1.8 by 12 scale. And we see that we're getting the separation we want in a kind of an integrated treatment stream at a small scale with real waters. And now let's scale it up to the next scale and demonstrate it for a month or two with an industrial partner in the right setting. I think there's a formula that works there. I think where we get in I think where we get in trouble is where we expect to skip steps. I don't think we can jump straight from like we've seen this really good separation to building a pilot. And I think when our sponsors like we have sponsors, so we have people who decide if this is a good project or this is a good project. And I think their wisdom is so massively important in making things successful. And so we need to help educate them and to make it work.
For sure, research has its place, yeah, in the ecosystem. There are different kind of researchers, yeah, and different kinds also of interconnecting points between the industry and the research, and we need to take into consideration every point in the map in order to make the whole thing work. Yeah.
Yep. We
Is
have
there
it. Yep.
is there any, and speaking about points in the map, do you think that there is some like a point that needs to be emphasized more in the future? Like, for example, I don't know, general interconnecting generalists that can help translate from one side to the other.
I think there's definitely a need for um, there's a need for generalists. So I think there's a couple places that I think we need more technology development. I think people have lent themselves. I think there's a lot of analysis in the water treatment space and a lot of support for analysis. I think we need an equivalent amount of support for technology developers. And I often see technology developers just as kind of coming in a couple flavors. One being the the individual trying to develop a unit of operation, a new unit of operation, like adding a new card to deck, adding a joker to the deck of cards we already have, and that we're shuffling through right now to make it work, like from adding a scalant to adding the anti-scalant to adding the biocide. Those are cards we have in the deck. And we need new cards. And then we need that generalist that integrates things. Absolutely. We need that person who can put the deck together in the most efficient way. There's examples of AI I'm not always a fan of AI. I think people use AI to sell a lot of things, but I know of at least one company out there that is using AI to increase the efficiency of RO plants, and they're getting like 5% improvements or better, and that's spectacular. A 5% improvement is amazing. So I think we need both, and I think we need to strengthen the interconnection between the two areas. Over the past 3 weeks, I've been to a water meeting. I went to Columbia, which is the oldest mining school in the United States, School of Mining in the United States, and several meetings on mineral recovery, critical materials. And there's huge potential for interconnection between all these efforts.
Yeah, yeah. We certainly need better translation between all the
Yeah,
relevant parties. Um, do you think there's going to be a disruptive technology in the next years that can
I
transform
think
potentially the case of brine valorization? You
I
don't
think
have
there's
to
a hunger
name it.
for it. I absolutely think there's a hunger for it. I was at a meeting, and there's like, what about this? So I'll name something. So I work in solvent driven separation. So I work in two different types of solvent driven separations. I work in uh, where the water is moved into the aqueous phase, leaving just solids behind, and we can get really pure water. We can take, if we're doing this with sodium chloride, we in the water we extract and then recover, we get down to 250 parts per million. We had a paper come out recently that says we can basically do ZLD for the same cost as with the solvent process as MED. And the cost in the process, the innovation and the cost in the process is in the DME recovery. So we can recover 99.9995% of it in like 10 minutes. So it's the recovery that's the real value. Um, it's also the cost. So in the ZLD process, it comes out to roughly the idea is it's going to be cost about as much as MED at scale. We still need to scale it up and demonstrate that, um, but that's exciting. But if we can do solvent-driven fractional crystallization, and so that's where the water doesn't move into the organic, but the organic moves into the aqueous and induces precipitation. It uses 20 times less DME. So instead of pulling 8% of the water into the DME, we have 38% of the water going into the aqueous, which is 20 times less DME. And it can induce a huge recovery of minerals. If you're looking at like calcium sulfate, we can get 99% of the calcium sulfate out that way relative to saturation. So it can just knock it out. And so that's really exciting. Right now, we can do a 12% recovery of sodium chloride, but there are steps that we can take to improve that, and that's what we're working on right now, is basically bringing that recovery or bringing the concentration down to increase the recovery of something like sodium chloride, which then you could imagine a treatment train where you have seawater reverse osmosis, maybe even osmotically enhanced reverse osmosis, taking it up to high concentrations, and then having our technology where we take the sodium chloride down to a level where it can be sent back through the process, where the aqueous can be sent back through the process, and we get solids out.
Are both options right now in lab or pilot scale?
They're in the lab.
Yes, lab.
So we're not working at like 1 mil efforts. Like we're well beyond one mil efforts. We have a system that can do 70 liters at a
Okay.
time, but it's a batch reactor. And ultimately, we don't want to do this batch. We want to do this continuous. And so a lot of our experiments are done at the 50 mil to 100 mil scale, and almost always we're working um, with real solutions, like not environmental solutions, industrial solutions. Those we're bypassing. Well, we do some experiments with pure minerals to understand the process, but that's really where we are in the effort. And so but we're in a position where the right sponsorship would take us to piloting within months. But it, it takes the right sponsorship to do that. So um,
It
yeah,
takes the right
it's
sponsorship
in.
and the right partners that understands how to scale up, right? Scale up, especially in
Mhm.
all the technologies.
Yep. Yep, it's an essential. That's an essential step, and what that looks like. And you were talking about like there's different uh, actors. There's users with end water needs. There's companies trying to do mineral recovery that have. There's companies that are doing mineral recovery from water. There's companies doing it from like ores, and then there's companies that help those. There's engineering firms that design systems, and then there's a handful of startups type companies that are innovating and developing, and every one of these companies has a role. And how we translate kind of these new ideas into the market is exciting.
Do you think that there should be a better coordination of all these efforts instead of doing things in parallel? Or is it just
I
another
think
competition?
I it's how I it's a really good question. I don't know. I mean, like there I think we could use the we have some good efforts within the United States. So we've got NAUI, the National
Yeah.
Alliance for Water Innovation. They're doing really good work. Peter Fisk and Megan Motter are doing some fantastic stuff. But I think we need more. I don't think that is, if you look at it, that is our kind of like what the U.S. is doing in water treatment. And it's not all technology development. A lot of it is analysis that they're doing. So we only have so much technology development going on. Um, so I think if we push some more resources that way, we could have really changed the way things are done. And I think there are spaces that are appropriate for kind of like doing foundational work and doing foundational work, doing innovative work, and then doing early technology development, let's say pre-pilot, um, that would develop technology to the point where industry could come in and pilot well, and like, and actually know what they have to do a pilot, like, and not have projects kind of just slam together.
Well, well, for certain, at some point, the problems will be so high that will force us to find a solution to all kinds of these problems. I
Yep.
just hope that I won't see it in my lifetime. But
I,
um, I would like to bring up again the economy of scale when it
yeah.
comes to brine valorization.
Hmm.
So, um, when you mentioned, for example, the solvent crystallization,
Yeah.
right?
Yep.
So you absorb water and you leave essentially everything behind as a
Yep.
dry mass of salts. Do you think it could be like a good way to do brine valorization, for example, because it cannot be applied in small or medium scale, right? You can have skin
No.
valorization, as Hugh Fleming said it. Yeah, you can have like a partial valorization for one or maximum two components on each side, but not for all the materials, especially for the critical ones. So
So
how do we overcome this?
this is super interesting. You brought up a couple different issues, and so there are two scale questions that are jumping out at me in what you mentioned, and one of them is, okay, the scale of the technology. So if you look at a crystallizer, crystallizers love to be huge pieces of hardware, like they're giant. They're very, very large. And
Yep.
so the DME process can actually scale like RO. So it can be very, very small.
Hmm.
And you can scale it to whatever scale it needs to be. And the cost isn't necessarily directly tied to being very large. Like crystallizers, baffled crystallizers, you make them very, very large to be cost effective. We have the option of having like many or just a few, depending on where it is in the process. The second element of scale is the size of a resource. And historically, people don't want to build a recovery effort unless they have a very large resource. And
Hmm.
so you get into a lot of conversations in kind of the recycling space right now about the hub and spoke approach, where you have spokes where they're doing small scale collection, like an enrichment or valorization at various places that then feed to a centralized processing facility. And there's discussions on making that centralized processing facility flexible, so it could accept from like acid mine drainage, or it could accept from a recycling stream, or it could accept from a real ore or whatnot. And so that's one strategy of dealing with these smaller resources. Um, and so there's a lot going on in those questions. And the last thing is with the critical materials, they're usually secondary products. So like gallium. So you're producing aluminum, and gallium is parts per million in the aluminum stream. And it's not always cost effective to recover it, but it's absolutely essential for the semiconductor industry.
Yep.
Like we need that. But it's not controlling the mineral recovery process, and a mineral recovery effort might ignore it. There's an example of a facility in Utah that was making mag chloride to put on roads as a de-icer.
Yep.
They were putting $100 million plus per year of lithium chloride onto the roads. More than $100 million a year was going straight onto the roads of the Western United States simply because it was a minor component and it didn't make sense for them to do lithium recovery. They've visited this subject at least 3 times, and in the last year they decided to pull the trigger and they're gonna build the lithium recovery unit, and uh, and
That, that
now they're gonna recover it.
that's super interesting, and you also have a lot of other critical minerals, I guess, like rubidium, for example. In the past, it was like lithium; it was considered waste, right? And suddenly, in the last decade, I hear it everywhere.
Yeah,
So I think we still have a lot of way to go, yeah, and a lot of other interesting minerals to cover.
yep,
Um I think we don't have a lot of time, but I would like to thank you very much
yeah,
for making the online appearance. I will put in the description in LinkedIn, YouTube, your contact details so that people can reach out to you for the DME process. Yeah, I think it's
yep,
one of what you're doing in your team, Idaho Lab is super interesting, and I think it needs to be promoted more. Let's say in
yep.
the ecosystem of the water industry. Um, Anything I can do to help goes beyond my question. You can just, of course, always go, always call. I would like to thank also the Idaho Lab for giving you the access to present yourself and your work online. Yeah, that goes without any question. And I hope that somehow we can all be more interconnected in the future for solving brine valorization.
Yep. Yeah, absolutely. Thank you very much. This is a ton of fun.
I'm happy to do it many more times in the future. But for now, I want to wish you all have a nice day and best of luck.